Good morning, everybody. Happy Monday. I have to apologize for the late upload. I had this videoed once, and the video crashed and wasn't working, so we're going to try it again here. So sorry this is up a little bit late today. First of all, there were some problems with the reading assignment. So if you look on the announcement today, you'll see that if you were doing the modified reading assignment, which is only certain people in the class, that document was having problems. So just go to the regular assignment and just do the odd numbered questions. That'll cut your assignment in half if you're doing the modified. Everyone else do the regular one. Today we're talking about gravity, and gravity is a force that acts on objects. We think of forces as pushes or pulls. Most forces we think of things actually in contact and pushing or pulling something. Gravity is a force that acts on stuff without touching it. It's just two objects can be apart and still have a force pulling them. Gravity is fascinating. We don't understand a lot of things about gravity. We know it's there. We can measure how strongly it pulls on things, but why gravity works at all, for example, we don't really know. I mean, that's the brightest minds in the universe have had ideas of why gravity works, but we don't really know. Well, for today, this is going to be a section notes, and this is just part one. There will be a couple parts to this. I'm going to keep this fairly short so that you can get notes written down as well and have time to finish up your reading assignment. So make sure in your notes that gravity is your title. You'll want to do this so that you have them to reference when you do your quiz, just to make it easier. And of course, when you do your quiz, you can always come back and rewatch this video as you're doing the quiz. So take your time on those quizzes. A lot of people are rushing through them and not checking their answers as they're going, and so their scores aren't what they should be for an open note quiz. Well, first of all, you'll want to write this down. You can either write it from the video here, or I have the slides posted up on Google Classroom. But gravity is a force of attraction, meaning things are pulled together. It's an attractive force between any two objects. Doesn't matter what the objects are. If you have two objects, they are pulling on each other. There's a force between me and this computer that I'm looking at right now. It has gravity and I have gravity, and we're actually pulling towards each other. Now, not very much. There's a very small amount of gravity. We don't start sliding towards each other because there's friction keeping us where we are from the floor and on the table. And of course, the Earth's gravity is overpowering both of us and pulling us down. But if we were just floating out in space, me and my computer here, and there's nothing else around, we would slowly float together because we actually both have gravity. Now, the amount of gravity that an object has depends entirely on two things. First is how massive the object is. Remember that mass is how much matter is in an object, how many atoms and molecules. Slightly different than weight. Weight is how strongly gravity pulls on something, but mass is just how much matter is in there, how many atoms and molecules. So the more atoms and molecules something has, the more massive it is, the more gravity it's going to have. That's why when you go to the moon, you weigh less. The moon has like a sixth as much mass as the Earth, so it has about a sixth as much gravity. You weigh 6 times less on the moon than you do on Earth. It has less mass there. More massive objects have more gravity. Obviously, Jupiter. If you were to go to Jupiter, you would weigh a whole lot more. In fact, you'd weigh so much, you wouldn't be able to stand up. The force of gravity would be so strong that your own body weight, your muscles, couldn't apply enough force to keep you standing upright. That's how strong it is. More mass is more gravity. The other thing that factors into how much gravity there is the distance between the objects. As objects get closer together, the gravitational force between them is stronger. And the further away things get, the force gets weaker. So if you go in a spaceship and you take off and you're leaving the Earth, so here's the Earth. Where did my marker go? So you're leaving the Earth. As you get further and further away, the gravitational force gets less and less. So mass and distance are the two things that affect the gravity. So make sure you write this slide down, either from the video, pause it, or go to the slides in Google Classroom, get this slide written down. Probably also want to write this slide down just as a refresher. Remember that mass and weight are different. If you go to somewhere else that has a different amount of mass and different gravity, you're going to weigh different amounts. You go to the moon, you weigh less. But your mass is still the same. You still have the same amount of stuff in you. And gravity is everywhere. So again, everything has gravity. You have gravity. The earth has gravity. A car, a book, and even something as small as an ant or smaller has gravity. You have a whole lot more gravity than the ant does, but both still have gravity. More mass, more gravity. Now, this is an interesting question. So when you jump into the air, what happens? Well, as you guys know, you jump up. So here's our Earth. Here's you. Let me make that a little bigger. Hopefully this doesn't crash it. You jump up into the air. So now you're up here. You're, of course, way bigger than you should be in real life. And, of course, you fall back down. But did you know that when you jump into the air, you actually pull the Earth up to you? So you are here, and you jump, and you go up several feet. And the Earth actually goes down a little bit, like this. You push the Earth away from you. Now, not very much, right? Because your mass and the Earth's mass are so different that, for the most part, it's you moving, and the Earth moves so small you can't measure it. We're talking like 1,000th of the width of an atom. An incredibly small amount, so it's pretty much zero. But in reality, you jump, and you push the Earth away from you, and then since you have gravity, you pull the Earth back to you, just like you get pulled down to the Earth. Difference is you move several feet and the Earth moves up to meet you, again, like 1,000th of an atom's width. But kind of crazy, right? You have gravity, so you actually do pull the Earth back to you. Just a tiny, tiny little bit. Not measurable, but a little bit. All right, well, we know that the amount of gravity depends on the mass of the object. Okay, well, the sun is billions of times more massive than the Earth. So how come, as you're standing on the Earth, let's redraw here. So here's the sun. Here's the Earth. If you're standing right here, how come you don't just get pulled right off the Earth and get pulled into the sun? Why not? The sun is billions of times more massive, has billions of times more gravity. So why don't you get pulled off the Earth and just get sucked right up to the sun? Well, remember that the second thing that affects how much gravity is the distance between the objects. So, of course, the sun has way more gravity, but you are so close to the Earth compared to the sun that, you don't get pulled off because the overall gravity on the Earth is stronger because you're close to it. Gravity's everywhere. It doesn't matter how far apart two objects are. There's always a gravitational force between them. You don't need to write this slide, by the way. You don't need to. But it's going to be a very weak attraction. There is gravity between you and the stars out there, but they're billions of light years away, millions of light years away. So, it's such a small attraction that doesn't actually do anything, but it's there. Just a tiny, tiny bit. Okay, well, if distance makes a difference in the amount of gravity, let's say that you fly a spaceship and you go exactly halfway between the Earth and the sun. I tried to make this halfway. Well, what happened? Would you get pulled to the Earth, get pulled to the sun, or since you're halfway, would you stay right in the middle because you'd be balanced? What do you think? Think about it for a second. Well, in this case, you get pulled toward the sun because if the distance is equal, if you're the same distance from the Earth and from the sun, well, now the one with the bigger mass is going to win, right? So that's where the sun's billion of times more mass is going to pull you that way. You're going to get pulled towards the sun. Well, then where would you need to be? What if you wanted to be balanced? What if you want to be pulled equally to the earth and equally to the sun, so you stayed put in between them? Well, you need to be somewhere quite a bit closer to the earth to balance it out. Get close to the earth so that it has more force, but the sun's greater mass is pulling you, and you'd be balanced somewhere in there, right? A few thousand miles or something from Earth, a few million miles from Earth. Well, we already know from our lab the other day that if you take objects and you drop them, they will fall at the same rate if you can ignore air resistance. A hammer and a feather fall all at different rates because of air resistance, right? Get rid of the air, they'll fall at the same speed. So make sure you write this. If gravity is constant, two objects are going to fall at the same speed as long as you ignore the air resistance, as long as you get rid of the air. So if you're on the moon or in a vacuum chamber, or you just ignore the air resistance through the shape of it, right? Make it more aerodynamic. The objects will fall at the same speed because of their inertia, as we talked about the other day. You also know that if you drop something, it will fall faster and faster and faster and faster because the forces on that object are not balanced, right? So you take a ball, you drop it off a cliff, and there's this force of gravity down and just a tiny bit of air resistance up, and so it goes faster, faster, faster because the forces are unbalanced, and so it's accelerating down, right? You can see here it goes faster, faster, faster. This is an interesting question then. What if you took a penny? Maybe you've heard this before, but what if you took a penny, you went up to the top of the Empire State Building, a really tall building, and you threw the penny off. And there's somebody standing down at the bottom of the building, and that penny goes, and it bonk hits him on the head. Could you kill somebody by doing that? Would that bullet go faster and faster and faster and faster until it was going as fast as a bullet and killed him? Well, we will explore that in part 2 of our video. For now, watch this video, maybe rewatch it if I went too fast, and get the notes down on the couple of slides that I told you to write down. There should have been like 3 or 4 slides to write down in your notes. Make sure you finish your reading assignment, and I will put the second part of this up on Wednesday.